Hello and welcome to the YouTube channel D Creations Resources. We are looking at different concepts from science, especially physics, maths, etc. Now, today let us talk about vibrational spectroscopy. So, we have already talked about electromagnetic radiation in one episode, and we have also spoken about spectroscopy in another episode. And so, you can refer to it if you want to refresh those concepts. But basically, we know that spectroscopy deals with the interaction of electromagnetic radiation with matter. So, consider a sample on which electromagnetic radiation is incident. Now, suppose certain energy quanta from electromagnetic radiation is absorbed by this sample, then depending on what that corresponds to, what wavelength or frequency of the electromagnetic radiation it corresponds to, there would be transitions between different kinds of energy states which are induced in the molecules of the sample. So when you are saying that it is interacting with matter or it is interacting with sample, basically it is interacting with the molecules in the sample, right? And molecules of course consist of atoms. So that is the core interaction that is happening. Coming back to our discussion, suppose absorption has taken place, then in case of spectroscopy, we are basically recording these absorption changes with respect to parameters such as frequency or wavelength or wave number corresponding to the electromagnetic wave. So this particular wavelength or frequency or wave number is varied over a given range. And what is a spectrum? Spectrum is a plot of, say in this case, absorption of energy versus either frequency or wave number or wavelength, whatever may be the case. Now we are talking about absorption here. Of course, there could be other situation. There could be even transmission, for example. But spectrum is basically this plot which reveals certain information. So if it is a plot of absorption of energy versus frequency, suppose, and then it might be showing a number of absorption bands whose characteristic position, intensity, width and shape are going to give us important information about the particular sample. The electronic structure of the particular sample can be determined using this experimental technique of spectroscopy. Now, vibrational spectroscopy will correspond to a certain part of the electromagnetic spectrum, mainly the infrared. And usually, when you see the plot, you would see that on the x-axis you will see wave number. So what is a wave number? Wave number, which is also denoted as nu bar, it is the number of complete wavelengths contained per unit length. So suppose the length is 1 centimeter, and if you say that the wave number is 20 centimeter inverse, this means that there are 20 complete wavelengths in 1 centimeter. Now, since a wave number has the dimension of reciprocal centimeter, that is centimeter inverse, it is obvious that wavelength and wave number are going to be related inversely. In fact, wave number nu bar is 1 upon lambda. For example, if you consider radiation of wavelength 100 nanometer, can you calculate the wave number? You can just pause the video, calculate it, and then cross check with the answer that I am giving. Okay. So, wave number, as we mentioned, is 1 upon wavelength. So, 1 upon 100 nanometer. Nanometer, as you know, is 10 raised to minus 9 meter. So, 1 upon 100 into 10 raised to minus 9 meter. Right? Or if you are suppose converting it to centimeter, then it would be 100 into 10 raised to minus 7 centimeter. So that the answer is going to be 10 raised to 5 centimeter inverse. This is the wave number corresponding to the radiation of wavelength 100 nanometer. Now, it is also obvious that like frequency, wave number is also directly proportional to the energy of the radiation. Now, coming to the region associated with vibrational spectroscopy, it is the region of electromagnetic spectrum if you are able to recall, the electromagnetic radiation, basically these are the transverse waves consisting of electric and magnetic fields vibrating perpendicular to each other and to the direction of propagation. And of course, in free space, these waves are propagated at the speed of light. And in a nutshell, an electromagnetic field is an oscillating electric and magnetic disturbance that spreads like a wave or spreads as a wave through the vacuum. And obviously it has two components. The name electromagnetic itself tells you that it has two components: an electric field which acts on charged particles, be it stationary or moving, and a magnetic field that acts on moving charged particles. Now, to speak quantum mechanically, of course, here we need to talk about photons, right? So this is particle-like description of electromagnetic energy. And the intensity of the radiation, for example, can be determined by the number of photons in a ray. So if the ray is very intense, it has large number of photons. If it is not weak in intensity, it has a few photons, right? And in that context, the energy of each photon is related to its frequency. E is equal to h nu, right? So h is Planck's constant. So very well known relation, E is equal to h nu. And this will also help us understand how high or low energy of infrared radiation is as compared to the other regions of an electromagnetic spectrum. So an electromagnetic spectrum is going to consist of several regions, right from radio frequency region where the energy changes arise from the reversal of spin of a nucleus or electron, and the spectroscopy techniques that utilize this region are nuclear magnetic resonance and electron spin resonance. Then there is microwave region. Here the energy changes arise from transitions to higher energy rotational levels of molecules, and electron spin resonant transitions also occur in this region. And the technique of spectroscopy associated here is rotational spectroscopy. Then of course comes our infrared region. Here the energy changes involve transitions between the vibrational levels of molecules, and the technique associated is of course vibrational spectroscopy. Apart from that, you have visible and ultraviolet region where the energy changes involve valence electrons of molecules, and the technique is electronic spectroscopy. Or then after that there is X-ray region where the energy changes involve the inner electrons of an atom or molecule. Or last there's a gamma ray region where energy changes involve the nuclear excitation, and so on and so forth. But our focus when it comes to vibrational spectroscopy is of course the infrared region of the electromagnetic spectrum. We'll look at the details in the next episodes. Thank you.